indicators are simply weak organic acids and bases that gives out a color when they deprotonate or when they are being protonated. Okay, so for example, look at this indicator now. This indicator might have a certain color here, but when it has been deprotonated or the proton has been removed, okay, a certain color of the indicator will also have here. So indicators, they give out colors upon protonation and deprotonation. Examples of indicators will have phenolphthalein, methyl orange, methyl red, and there are a lot of them. Okay, so I know you know most of these things because you have used them for your titration and the rest of them. All right, it's good. Now the next thing we'll talk about here is, but take note, this thing happens at what? Equilibrium. At equilibrium. Okay, at equilibrium. So now the next we'll talk about is the buffer solution. The buffer solution. Okay, buffer solution. So what is a buffer solution? What is a buffer solution? A buffer solution is a solution that can resist a change in pH when an acid or a base is being added to it. When a small quantity of an acid or a base is being added to it. Now these buffer solutions are made up of their acid and their conjugate what? Base. Okay? A buffer solution is made up of an acid and its corresponding what? Conjugate base. Or you can say a base and its corresponding what? Conjugate acid. Example, we have this acid. Look at this acid. This acid is ethanoic acid. The conjugate base of this ethanoic acid is actually the sodium ethanoate. Okay, this is the conjugate base. So a combination of these two can be used to prepare a buffer. Okay, we also have ammonium hydroxide. The conjugate acid for this is, I think, we have ammonium chloride. So we can actually use this combination to prepare a buffer solution. Take note, a buffer solution can be prepared, is made by using the corresponding acid and the conjugate base. So this is the conjugate base, this is the acid, right? This is the base, this is the conjugate acid. So that is how so this buffer solution is important because you can use it to actually resist, control the quantity of acid that can, so that the acid will not alter the value of whatever you are doing. So the pH can be maintained at a specific particular place. So the buffer is like how will I put it? The buffer solution is like something that we use to control or resist the change in the pH of a solution when an acid or a base is being added to that solution that you are using for maybe one or two things. So that is exactly what a buffer is used for. So now this buffer solution is governed, or the equation that is used to govern this buffer is called the Henderson equation. Okay, the Henderson equation. So this Henderson equation is giving us pH is equal to minus log Ka, which is the pKa of the acid, plus log salt over acid. Okay, so that's the equation that governs a buffer. So we can also write this equation as saying that pH of this buffer is equal to minus log Ka plus log anion all over cation. So that is the equation that we use that governs the buffer. Okay, so we can also write it to be pH of an equation is negative log Ka plus log salt all over base. So we have this. So these equations are important. So with this, we can also relate it to what the general equations for pH. Right? We remember we have that pH plus POH is equal to 14. So we can also evaluate the POH from here. Once we know the pH, you can get the POH of this same buffer, depending on what you are trying to solve. So note, this equation, remember that we have two types of buffer. We have acidic buffer and basic buffer. So For the acidic buffer solution, the equation that governs it is this. Okay? While for the basic buffer, the equation that governs the basic buffer is this. So take note. So this is for acidic buffer, this is for basic buffer. So these equations are used to govern the buffer solution. So take note, for this is an acidic buffer. If I want to prove an acidic buffer, an example, this is an example of a basic what? Buffer. So take note of these equations I've given you on the board. So we can use problems to calculate. We can use some calculations to illustrate this the more. So let's look at this question on the board. There are two questions here. Let's start with this, okay? So at 25 degrees C, the hydrogen ion in pure water is this value. What is the pH? So solution, you know that the pH of a solution is minus log hydrogen ion concentration. So this guy was dissolved in pure water, so this pH will be just definitely this. So the pH of this solution will be minus log, impute the value, 1 times 10 to the power of minus 7. So pH of this guy, your calculator minus log of this will give you 7.0. Note, pH does not have any units. So when you get this pH, you just leave it like this, okay? Now since it is 7, it means that this pH is a neutral, so it's a neutral solution. The solution is a neutral, the solution is neutral. How do we know the solution is neutral? From your pH scale. Remember, from your pH scale, we have from 0 to 14, okay? So the middle point is 7, which is the neutral point. But from here to here is alkaline, okay? From here is basic, or you can see the word basic, okay? While from here to here is what? Acidic. So pH 7 at the center is neutral. This is neutral. This is neutral. So because we got 7, this is neutral pH, okay? Example 2. Compare the strength of these two acids, A and B. Okay, so the two of them are acids. So which one is stronger? For us to get the stronger acid, you have to find their pKa first. Because the lower the pKa, the stronger the acid, okay? You can also use their Ka to also solve it, okay? But most of you might not know which one is smaller and which one is bigger. So just get the pKa. So the pKa for A, the pKa for the first one, which is A, is minus log the Ka value, 1.8 times 10 to the power of minus 5. You close. So the pKa for this, for A, will be, let's solve for pK. So if I press minus log of 1.8 times 10 to the power of minus 5, you will get 4.74. Okay? Then for B, the pKa for B will be minus log the concentration of the B, which the Ka for the B, which is what? 4.5 times 10 to the power of minus 4. So if you find this pKa for the B will become 3.35. 3.35. So the smaller, the lower the pKa, the stronger the acid. Okay, so because of that, B is the strongest with respect to, because the pKa for B is 3.35, while the pKa for A is 4.74. So this is a stronger acid to the one on top here. Calculate the pH of a 0.1 molar acetic acid. This is the Ka. Okay, so solution. How do we go about this? Remember what I told you about weak acid. For weak acid, this, what they gave you here is the concentration of the acid, okay? So for us to find the concentration of the hydrogen ion, we have to find the square root of the Ka multiplied by the Ca. The Ca is this, the Ka is this. So hydrogen ion concentration will be square root of 1.8 times 10 to the power of minus 5 multiplied by 0.1. So when you find this value, you're going to have the hydrogen ion becomes 1.34 times 10 to the power of minus 3. Minus 3 capital M, okay? So we can now go ahead and find the pH, okay? So pH is equal to minus log hydrogen ion concentration, okay? Minus log hydrogen ion concentration. So which is equal to minus log this value, which is 1.34 times 10 to the power of minus 3. So when you punch this value, the pH of this solution will be 2.87. So this is acidic, okay? It's an acidic solution. An acidic solution. So number 2, find the pH of a 0.02 molar of sodium hydroxide. So remember, we are looking for pH, but what was given is a base. So we're going to find the pOH first. So pOH is equal to negative log of the hydroxide ion concentration. So from this solution, the hydroxide ion concentration is 0.02. Okay? Why is 0.02? Because there is just 1 mole of this guy in this solution, so it's going to just be 0.02. So we now simply say pOH is equal to negative log this value 0.02. So when you punch the negative value of that value, the negative log of that value, which is there looking at us, so you're going to have the value to be 1.7, okay? 1.70. So but this is not the answer. We're looking for pH. So remember that pH plus pOH is equal to 14. Then pH will be equal to 14 minus what? pOH. Okay, so pH will be equal to 14 minus 1.70. So which we are going to get the answer to be 12.30. So this pH value means that this solution is the solution. It means that the solution is basic. Why? Because from the pH scale, I told you about if it's greater than 7, it is going to be basic. If it's less than 7, it's going to be acidic. Now take a look at this question on the board on buffer. Calculate the pH of a buffer prepared from 0.1 molar acetic. So this is the concentration of the acid, okay? And 0.2 molar sodium acetate. Sodium acetate is the salt of this acetic acid, is the salt. Sodium acetate. Remember that the salt is formed when a replaceable hydrogen is replaced with what? A metal, such as sodium. Okay? So the formula to calculate this is pH is equal to pKa plus log salt all over acid, their concentrations, okay? This one has already been given to you. But remember that if this one was not given, if they say they didn't give us the pKa, they gave us the Ka. Let's say they gave us Ka. So we are going to use this Ka and find this pKa. How? Remember that pKa is minus log of the Ka. Take note of this. So in case you are not giving this pKa direct, you can be given the Ka, you can find the pKa and then substitute it here and solve. Okay? So take note of what I just did here. Now, just put in the values. pH is equal to pKa is 4.74 plus log the salt. The value for the salt is 0.2. 0.2 all over that of the acid is what? 0.1. So you solve this, pH is equal to, when you solve this, the whole thing here, I think you are going to get the answer to this question will be 5.0. So that's the pH for this guy. So what we need to just divide this, find the log, then add it to this. That's the answer. For this solution, the same thing, okay? But this time around, you have to be very careful. He said, calculate the pH of a buffer solution containing this for the base and containing this for the salt, okay? This is the base, this is the salt. So because a base is mentioned, you have to find the pOH first. The pOH of this buffer is pKb, which is the that of the base, plus log salt all over log acid. No, base. That's how to get the pOH. So when you get the pOH, you can now get the what? The pH. I'll show you how to get it. So pOH is equal to the pKa. Okay, sorry. Yeah, this is the pKa. The pKa of this ammonium hydroxide. Okay, the ionization constant for this guy is this value. So we have 4.75 plus log salt. Where is the salt? Ammonium chloride, 0.1. So we're going to have 0.1 all over that of the base is 0.25. 0.25. So when you divide this, add to this, the pOH will be equal to 4.35. 4.35. But we're not looking for pOH, we're looking for pH. So pH is equal to 14 minus what? pOH, right? So that pH will be equal to 14 minus 4.35. So the answer to this question will be 9.70. So that's the pH of this solution.